Okay, I think we can begin. It's time for our third talk, and I should mention that after this talk, there will be a 30-minute break. But our next speaker is Kai Smith from Indiana University, and he will speak on character varieties and singular instanton homology.
Great, thank you, and thanks for giving me the opportunity to speak. Yeah, so I'll be talking about singular instanton homology and what kind of information we can get about it from methods coming from character varieties. So we'll start with singular instanton homology, which I'll mostly abbreviate just to instanton homology. And it's a knot homology theory, which was defined by Kronheimer and Mrowka, and it'll be denoted by I natural of K. And it has two important features. The first is that it detects the unknot. So if the instanton homology of a knot is the same as that of the unknot, then you know that knot is actually the unknot. And the second important property is a spectral sequence that comes from Khovanov homology of the mirror to the instanton homology of K. And putting those two together, Kronheimer and Mrowka proved that actually Khovanov homology detects the unknot. And this is a fundamental fact about an important knot invariant. And so it's worth trying to understand singular instanton homology more. So I'm going to go through the construction, and I'll start with sort of some of the basics of gauge theory, which is how instanton homology is defined. So in gauge theory, you want to study principal G bundles over a space X. So I have this little schematic of a circle bundle over a circle. And to do that, one way to study bundles is using connections. So a connection is the data necessary to lift a path from the base space to a path in the total space in some G equivariant way. So if you know where you are along the path downstairs, that'll tell you which fiber you're on upstairs, but a priori doesn't tell you where along the fiber you are. And so the connection is the data you need to know that tells you where along the fiber to go. And one way to study connections is by looking at their holonomy. So if you do a loop downstairs, that tells you that your path upstairs will start and end on the same fiber, but not necessarily at the same point. And so you can take the difference between the start and the end and get an element in G, which sort of describes how far you've gone along the fiber direction doing this loop downstairs. So each loop downstairs in X gives you an element of G, your Lie algebra, or your Lie group. And then in the space of all connections, we're particularly interested in flat connections. So in general, if you have a loop downstairs and you wiggle it a little bit, the holonomy might change depending on how you wiggle it. But for flat connections, those are the ones where the holonomy only depends on the homotopy class of the loop. And so no matter how much I wiggle this, as long as I do homotopies, it's not going to change the holonomy. And so the space of all flat connections is equivalent to homomorphisms from pi1 of X to G. And so going one way is pretty easy to see. If I have a flat connection, I know any element of my fundamental group gives me a well-defined element of G, and so that gives me the homomorphism. But it turns out it goes the other way too. If I can pick for all my loops downstairs an element of G to be the holonomy, and I can prescribe a flat connection with that holonomy. And then the last important ingredient is the gauge group. So an element of the gauge group is just a fiber-preserving automorphism covering the identity on X. So here's an example where upstairs we can do a Dane twist along this blue circle. And so that gives me an automorphism upstairs, which preserves the fibers. And then the corresponding map down here is just the identity. And it's important to note that this acts on connections, right? So if I have here, I have a connection, it tells me how to lift paths down here, up here. But once I do the Dane twist, I get new lifts. And so I went from one connection to another connection. So now that we have these tools, we can construct the instanton homology. So we're going to start with a knot, and we're just going to work in S3 today, even though it's more general. But we're going to add something called an earring, which is, so if this is part of our knot, an earring is just a meridian of the knot along with an arc that goes from the knot to the meridian, which is in red here. So as part of the whole knot, it might look something like this. And in a second, I'll explain why that's there. And so what we're going to want to do is consider the principal SU2 bundle on S3. And we want to look at the set of all connections on this bundle, which are in some sense singular along the knot and earring. And then we want some restrictions on their holonomy. So if I have a meridian of my knot, the holonomy can be anything, but as I tighten it closer and closer to the knot, I want that holonomy to approach a traceless matrix in SU2. And similarly for this red arc, if I take a meridian of that, as I tighten it closer and closer to the arc, I want the meridian, the holonomy to approach negative the identity matrix. And this space is actually a little too big. And so what we're actually interested in is the space B, which is this space of all connections mod out by the action of the gauge group. And so we're going to study this knot by instead studying this infinite dimensional moduli space B. And the reason we added the earring is because without that, there's a trivial connection on the bundle, which doesn't play very nicely with taking this quotient. And so that'll make our moduli space very singular. And so one way to avoid that is adding this earring. Right, and so now we can study this space B using Fleur homology, which is just sort of the infinite dimensional analog of Morse homology. So what's playing the role of our Morse function is something called the Chern-Simons functional, which will take in a connection mod gauge and give you a real number mod the integers. And so then, just like in Morse theory, we can get generators by looking at critical points of the Chern-Simons. And so in this case, the critical points are actually going to be the flat connections in B. So with what we know about flat connections combined with the holonomy restrictions from before, this means any flat connection, the holonomy of any meridian of the knot is going to be traceless, and the holonomy of any meridian along the red arc is going to be minus I. And then we can ask about the differentials, and those will be something called instantons. These are connections on S3 cross R, and they satisfy something called the anti-self-dual equation. And then as we go to either sides of our R factor, our connection should limit to two of our flat connections. And so now we have a chain complex, and we can take the homology, and that's what I-natural is. And as you can imagine, this is a hard thing to actually compute. If I give you a knot, you have to construct infinite dimensional spaces, solve PDEs on them. It's not very practical. And so there's a conjecture by Attia and Fleur that says any instanton homology should have some corresponding Lagrangian Fleur homology. And so we're going to look at a proposed analog in the Lagrange Fleur world. And one of the benefits of that is that things are much easier to compute there. Not trivial, but easier than instanton homology. So here's an outline of what's called Pillowcase Homology by Hedden, Herald, and Kirk. And so we're going to start with our knot, just like before, and add an earring. But now we're going to find a sphere which intersects the knot in 4 points and use that to decompose our knot into 2 tangles, like this. And then it's important to note that there's a common boundary of these 2 tangles, which is this 4-punctured 2-sphere. Now, for each of these spaces, we can ask for its SU2 character variety. And that's just the space of homomorphisms from pi1 of x to SU2. And we want to mod out by the conjugation of elements in SU2. But that's not quite the space we're interested in. We want to impose some restrictions as well. So we want to restrict ourselves to homomorphisms which take any meridian to a traceless element of SU2, any meridian of a tangle or the punctures to traceless elements, and except for a meridian of this arc, just like before, it should be sent to negative the identity. And so what are the character varieties of these spaces? So for the 4-punctured sphere, we get this space called the pillowcase, which is homeomorphic to a 2-sphere with 4 singular points. And we'll unfold it like this so it's easier to draw on. And then for each of our tangles, we'll get some space. So let's say we get a circle for this one and an arc for this one. Now, since any homomorphism on a tangle complement can be restricted to its boundary, we're going to get maps from these character varieties, the blue and red ones, into the pillowcase. And so for the sake of example, let's say the circle maps in like this and our arc maps in something like this. Well, it turns out that the pillowcase is actually a symplectic manifold, and these other character varieties are mapping in as immersed Lagrangians. And so we can...
Sorry, so what's the blue circle and the red arcs are?
Yeah, so that's the traceless SU2 character variety of this tangle complement is the blue circle, and this tangle complement gives you the red arc.
Oh,
Yeah, so that's, again, looking at those homomorphisms from pi1 to SU2 satisfying some holonomy restrictions. Satisfying that meridian should get sent to traceless things.
thank you.
So, right, so now we have these Lagrangians in a symplectic manifold. One thing we can do is ask for the Lagrangian Floer homology, which is particularly simple since the pillowcase is two-dimensional. So we can get a chain complex by the generators will come from intersections of these two Lagrangians. In this case, there's 3. And we can get differentials coming from bigons, which are shapes like this, bounded by the red and blue Lagrangians. And then that gives you a chain complex, and we can take the homology, and that's what Hedden, Herald, and Kirk dubbed the pillowcase homology. One important thing to note that we'll talk more about later is that there's this choice of tangle decomposition. I could have picked a different two-sphere to decompose my knot along, and so they sort of conjectured that it's well-defined no matter where you pick this decomposition, and then conjecture that this homology should be equal to the Instanton homology. So there's one more thing I neglected to say so far, but as stated, neither of these really work, and we have to take into account some perturbations. So in singular Instanton homology, the Chern-Simons, as it's usually written, is not Morse for most knots. And in pillowcase homology, if we want to look at the character variety of a tangle, that's usually not really a manifold. Usually it's something singular, so there's always a one-dimensional component, but it might intersect something else or have higher dimensional components as well. And so we're not really going to get a Lagrangian if we have something singular. So in both cases, we can solve this by doing something called a holonomy perturbation. And the key data for a holonomy perturbation is some family of perturbation curves. So for the tangle we were looking at before, this is an example of a possible perturbation curve, just some family of loops in the tangle complement. And if you can find a suitable perturbation, that'll smooth out your character variety. So for example, this character variety on the left could smooth out, in one of these two ways, for example. And so for both cases in the Instanton and pillowcase homologies, you can always find some perturbation which will, make your homology computable. So let's compare so far what we have. So between pillowcase homology and Instanton homology, the generators of the chain complex have a natural equivalence. So an intersection in the pillowcase meant we had a homomorphism on each tangle complement, which agreed on the boundary. And so we can glue that into a homomorphism on the entire knot complement. And we saw before that this corresponds to a flat connection. However, for Instanton homology, we took flat connections and modded out by gauge. In pillowcase homology, we took homomorphisms and modded out by conjugation. And so you just have to check that these two quotients act the same way on both, and they do. Furthermore, these generators in both theories are Z mod 4 graded, and you can make the generators agree, the gradings on all the generators agree. But the bigons or the differentials are a little bit more complicated. So on one side, instantons sort of act as a interpolation between flat connections, and bigons also act similarly as an interpolation, but they don't necessarily satisfy the right smoothness conditions to correspond to an instanton. And so it's less clear if these two are equivalent. And so that's something we'll try to answer as well. So what examples had been computed? So Hedden, Herald, and Kirk could compute the pillowcase homology of two bridge knots. Those are almost trivial since a two bridge knot just comes from gluing together two trivial tangles. So those were fairly simple, but then more complicated examples came from torus knots, but they were only able to compute the pillowcase homology with certain tangle decompositions. And all the computations they did agreed with known or conjectured values of Instanton homology. So, which led them to conjecture that the two homology theories are isomorphic. And so one thing that I was working on was generating more examples by studying this tangle I have below, which I'll call T. And so one thing to note is that there's 3 boundary components. And so the character variety is actually going to be a 3-dimensional manifold mapping into a product of 3 pillowcases. But once we understand that, we can plug in 2 tangles, here and here to get a normal tangle with 1 boundary component like the ones we were looking at before. So I'll give a brief rundown of what this character variety looks like. So the first thing to say is that we're going to really look at the double branch cover of the character variety, but all the interesting stuff happens far away from the branch points. And so that's kind of good enough for now. And before we perturb, this is the character variety we get. We have a T3 intersecting 2 S2 cross S1s. So here's sort of my picture for it. I have this annulus, which I've shaded in, and I'm going to identify the 2 boundary components so that we get a torus. And we see these two spheres, and they're both going to intersect this annulus in a circle. And I'm going to take that whole picture and take the product with S1. And so we can see that there's 2 tori's worth of singular points, right? So on these 2 circles that intersect, once I take the product with S1, I get tori. And these are going to be, singular points in our character variety, which we want to smooth out by perturbing. And a neighborhood of any such singular point is going to look like, a plus times a D2. And so when I plug in tangles into 2 of our 3 boundary components, the character variety we get is going to be cut out of this larger character variety. So for example, somewhere along this interval, I might get a circle which intersects it. These, singular points here come from cutting out neighborhoods like this, and we get these pluses here too. And when we map our character variety to the pillowcase, the interval part will just wrap around in some way, but then a circle like this will fold in on itself, and both halves of the circle will get mapped to an interval like this. And then if I perturb the tangle T with the perturbation curve I showed in the last slide, each of these neighborhoods is going to smooth out so that it's either, this smoothing cross a D2 or this blue smoothing cross a D2, or in between, you'll get a saddle cross I. And so for every point on these singular tori, I can ask which way does it smooth when I do my perturbation, and I can color that in red and blue like this. And so if I want to know how a tangle smooths out after I've plugged things into the big tangle T, I can just look at each of these singular points here and see where along the 2 singular tori they came from and which way it's smoothed. And it turns out that whenever I have a circle like this, one of the singular points will always smooth the red way and one will always smooth the blue way. And so for our picture in the pillowcase, anything that looked like this is going to smooth in a way that gives you an X. So that was just a quick overview on what kind of goes into looking at that character variety. But what we get out of that is now that we understand that character variety, we can compute the character varieties and pillowcase homology for any arborescent knot. And that's just a knot made out of rational tangles, which are easy to understand, and copies of this tangle T. And so here's an example of a knot. And these boxes just correspond to the noted number of half twists. And if I put these circles here, you can see these circles cut out the diagram into rational tangles and copies of T. So this is an example of an arborescent knot. And the benefit of computing things with this construction is that, remember, to compute pillowcase homology, I had to choose a specific tangle decomposition. Well, I can just as easily compute the pillowcase homology using any of these decompositions. So for a single knot, I can compute the pillowcase homology many different ways. And it was conjectured that no matter how I do that, I'll get the same thing. But if I look at this example, the -3, 5, 7 pretzel knot, I can decompose it in these three ways, given by these circles, and the asterisk is just here to remind you where the earring is. So before I do anything, a result of Lobb and Zentner says that the rank of the Instanton homology should be somewhere between 11 and 15. But if I compute the Pillowcase homology with these three different decompositions, I can see that I get rank 15, 5, and 1. And so remember, it's Z4 graded, so these are just the ranks in each grading. So in particular, Pillowcase homology is dependent on the decomposition. So it's not really well defined, and that definitely can't be isomorphic to I natural. So what does that tell us? So first of all, going back to this kind of comparison, we knew the generators matched up between our two theories. And as much as it would have been nice for bigons and instantons to be equal, they're not. And so we just have to let bigons be bigons. But what does that mean? So even though the current definition of Pillowcase homology isn't well defined, it should probably be fixable. So the differentials were defined using these bigons, which is sort of the simplest data out of what's called the Fukaya category, right? So these Lagrangians in this pillowcase form a Fukaya category. The differentials we chose were just the simplest bit of data from that. And so by using more data from there, in particular, something called bounding cochains, I think it's hopeful that, you know, the definition can be tweaked so that it is well defined and hopefully isomorphic to Instanton homology. But secondly, even in its current state, you can still generate the chain complex of Instanton homology. And so this alone lets you get bounds on the Instanton homology. And sometimes with other bounds, that's enough to tell you exactly what the Instanton homology of a knot should be. And furthermore, it sheds some light on the spectral sequence from Khovanov homology to Instanton homology, which is, you know, it's sometimes sort of mysterious. So yeah, that is what I had to say. And thank you for listening.
Yeah, thank you. So are there questions for the speaker?
I do have a question.
Yeah.
Hi, Kai. I was asking you mentioned in theorem you proved that you say that the pillowcase homology depends on the composition. Yeah. So like, how do you prove that? Like you just took these two knots and you proved that the homology is different, or you prove that for every knot there exists to the composition that differ?
Yeah, so for this, all I really need to do is find an example. And so here's an example knot where different decompositions, I can go through the steps of calculating pillowcase homology and I get different answers. Okay. And so the reason you get different answers comes from the fact that these Lagrangians were immersed instead of embedded. And so that's sort of what that idea of bounding cochains should hopefully take into account. And so that's why there's kind of hope that that would fix the definition.
So it is true that for every knot, I can find the composition that gives me a different answer.
I don't know that for every knot. So especially if I'm just looking at pretzel knots, for example, one thing I noticed was that, all alternating pretzel knots, if I do these three decompositions, I do always get the same pillowcase homology. So I think it's possible that with certain restrictions, it's possible that your knot will always give you the same pillowcase homology no matter where you decompose it. But in general, it doesn't work.
Okay. And also I have another question. What do you mean with the 5-star on the second picture?
Yeah. So part of the definition was adding that earring. And so the little asterisk is just here to remind you that the earring is sort of on this part of this tangle.
Oh, so the star indicates the earring. Okay, yeah. Okay, cool. Yeah. Okay, thank you.
Yeah.
Are there other questions? More questions?
Sorry, I guess this is more of a general question about Instanton homology, but are there like nice concordance invariants derived from this, like there were for Heegard floor?
That is something I don't know a lot about, but I know that at least when they defined the singular Instanton homology, they also defined a like analog of the S invariant, S natural. So I would assume, I don't know too much about the details of it, but I would assume if they're going to call it that it would be a concordance invariant.
Okay, thank you. Thank you.
There are a lot of conjectures if you want.
Okay, anyone else? Otherwise, thank you, Kai, and all of us will thank you any way we can using our virtual tools.
Thank you guys for listening.